The title of this poster is Optimal Collision Avoidance in Swarms of Active Brownian Particles. My name is Francesco Borra, and this work was done in collaboration with Massimo Cencini and Antonio Celani. In biology, collective motion refers to a number of natural phenomena which are characterized by the interactions of several living organisms. And the most common approach in studying these phenomena is to start from observations from which some models can be built. And from a model, one can try to deduce what the biological role of a certain behavior is. However, it is also possible to use the opposite approach, which can be called the optimization approach. So one can start by setting a goal and then try to use some technique, for instance, game theory or machine learning, in order to understand what is the optimal behavior in order to achieve such goal. And if such behavior is observed in nature, it is a strong indication that it was selected by evolution for a reason. The optimization approach is also important for obvious reasons when trying to control the collective behavior of artificial agents or robots. But it is also important from a theoretical point of view because physicists employ a number of models, for instance, the Vicsek or Kuramoto models, in order to understand collective motion. However, it is not obvious that these models are optimal under any assumption. So the main topic of this poster will be how a swarm of agents should behave when agents are trying not to collide with each other in an optimal way. And we will study this problem in a simplified scenario of a system of n active Brownian particles moving in the plane, which will be called either particles or agents from now on. So all particles have the same linear velocity, and they are characterized by an angle or head in direction or orientation, and they are subject to rotational noise, but they can otherwise partially control their head in direction through a control, which can be called F, which can be interpreted as a torque. And since we want particles to avoid collisions, we can assume that when two particles collide, they pay a cost. And this cost is maximal when the collision is frontal, and it is minimal when the collision is collinear. So what particles could do is to use their control in order to avoid meeting each other. However, in any realistic scenario, we should assume that the cost itself that the control itself has a cost as well. And this can be interpreted in several ways. For instance, it can be interpreted as a power dissipation or as the cognitive cost of deviating from the no-control strategy, as proposed by Todorov. And both these interpretations suggest that the control cost should be quadratic in the control strength. So given these premises, we can formulate the optimal control problem of avoiding collisions as the problem of minimizing the total average cost with respect to the controls of individual agents. Now, the total cost is defined as the sum of costs paid by individual agents. And since you're minimizing this total cost, it means that no agent has any interest in lowering its own cost while increasing someone else's cost. And for this reason, this is a cooperative game from a game theoretical point of view. Moreover, since in order to avoid collisions you have to apply control, it means that there is a trade-off between these two terms of the cost when minimizing. And moreover, we have to make sure that while minimizing this quantity, the correct dynamics is enforced. And for this reason, we are performing a constraint minimization of the cost with the constraint that is the dynamics. And it is known that for constraint minimization, it is possible to employ the Lagrange multiplier formulation. And indeed, we can write a Lagrangian. The first term is the cost itself. Then we have a first multiplier for imposing normalization of the joint probability. And then we have a collection of multipliers, one for each point in space, which allows to impose the Fokker-Planck equation in stationary condition in every point in space. We could try to solve the problem in the most general framework. However, it would be very difficult. So what we did is to use two mean field assumptions, which allowed us to study the problem analytically. So the first assumption is agent-wise factorization of a joint probability. Now, this does not mean that agents are independent, but it means that they cannot interact with pairwise interactions, and instead they have to rely on collective observables in order to build their optimal strategy. The second assumption is spatial homogeneity, and it means that we can neglect the dependence on space and just focus on the orientations of particles. And if we consider these two hypotheses together, we realize that we are studying a uniform region within the bulk, neglecting the edges, and that we can reduce the formulation of a problem in terms of one particle quantities and where the single particle is interacting with a swarm in a self-consistent way. So I will now try to outline the main idea, And from the Lagrangian formulation, one can write down what is called the Hamilton-Bellman Jacobi equation in optimal control theory, which yields the optimal control. And remarkably, it is possible, due to the quadratic form of the control cost, to write down this equation in a linear way. And formally, this equation is a Schrödinger equation for a quantum pendulum, which must be solved for both eigenvalue and eigenfunction. And remarkably, all parameters in the problem combine into a single parameter h, which is the only parameter which appears in the end in this Schrödinger equation. And this parameter has a very clear interpretation, and for this reason we called it tradeoff parameter. And it weights the relative importance of collision and control costs. So the higher h is, the more collision are important with respect to control costs. Moreover, as a whole, the system is described by a polarization vector, which is the average direction of the particles, and this vector has a vectorial part, which is somehow trivial because the global symmetry can be, the global rotational symmetry can be broken in an arbitrary direction, which can be fixed to 0, and the important part is the scalar or the absolute value of the vector, which can be called polarization. And it can be determined in a self-consistency equation, which depends on the fundamental trade-off parameter h alone. So from this self-consistency equation, we can define the polarization as a function of h, and we have shown it here. And as you can see, there is a second-order phase transition with a critical value h equal 2 and critical exponent 1/2. And now, in the article, we provide an extensive statistical characterization of the system, but I will just focus on two particular regimes, which are the critical regime and the Gaussian or strong interacting regime. And in both cases, we could show analytically that the optimal control has this very simple functional shape, which is described by a prefactor and a sign. And it means that this simple model, which we can call sinusoidal, is a good approximation, at least in these cases. And this is interesting because it has a very clear Vicsek-like interpretation. So, for instance, we can briefly sketch the idea of this continuous and stochastic Vicsek model, which is presented in these articles. And the idea is the usual one. So you have a swarm of particles, and each particle tries to align with the average direction as computed within a certain bubble drawn around the particle itself. And as long as we are in the kinetic regime, which means that the velocity of the individual particle evolves much slower than the average much faster, sorry, than the average within the bubble, we can write down the approximated control in the following way, which closely matches the functional shape that we've found as a good approximation of the optimal one. So now we did proceed with a more detailed comparison, and the idea is that we should compare the optimal solution with the best among all sinusoidal models for a given choice of parameters. And so it goes as follows. So you can write down the control, and then which is characterized by a certain control strength key, and then for a set of parameters you choose the control strength which minimizes the average cost. Now, the interesting thing is that the best sinusoidal model depends on the same trade-off parameter h as the optimal one, and the polarization has the same critical exponent and the same critical point. And in a more detailed analysis, we could see that the critical behavior matches up to a small redefinition of the polarization in the strong coupling case, which means that collisions are way more important than control. Essentially, everything matches at leading order, and finally we did a general assessment of the comparison between these two models for general values of h. And for this reason, we plotted the difference between the optimal cost and the cost of a sinusoidal model and divided it by the optimal the cost of the optimal solution. And we did find that this is a universal function of h, and it is always very small. And this means that for any value of h, it is possible to build a Vicsek-like dynamic model which is close to the optimal one, at least in this mean field approximation. So as a conclusion, we did find that we can employ optimal control theory and mean field gain formalism in order to study collective motion, and with some assumptions we can even approach the problem analytically. And remarkably, it is possible to use a simple functional shape with a clear Vicsek interpretation in order to describe, to approximate this system, which suggests that simple algorithms, simple models may be employed in an optimal fashion in these kind of systems. And as an outlook, it may be interesting to go beyond mean field and to approach different kind of dynamics with the same formalism. And thank you for your attention.